So I hope you are seeing the PowerPoint presentation that we have discussed previously. Did we discuss in the class, or did I upload this as a recorded video, this section? Meenakshi or Lakshmi or Arvind, anyone who has seen this?
Yes, sir, a
Can you
recorded
please
version. It was there.
Okay, this was a recorded version.
Yes.
Okay, so you would have appreciated that the type 1 linear phase FIR filter, which is a symmetric odd filter, that could be used for designing any kind of filter. Whereas a type 2 filter cannot be used for high pass or band stop filter because of this reason, that omega equal to pi, you see the h of e for j omega vanishes to 0. So the type 2 filters can be used only to design low pass and band pass filters. Whereas the type 3 filters, you see that the type 3 filters have 0 frequency response at omega equal to 0 and pi, making them ineligible to be used for designing low pass or high pass filters. So they can be used only to design what are known as band pass filters. We cannot use them to design low pass filters or high pass filters, and therefore we cannot also use them to design band stop filters. However, you can use them to design band pass filters, and typically they are used to design two kinds of such filters, which are known as Hilbert transformers and differentiators. So type 3 are mainly used to design Hilbert transformers and differentiators. We will see some worked examples later. Likewise, type 4 cannot be used for designing low pass filters because of this reason, and you can use them to design Hilbert transformers, but later we will see that type 4 cannot be used for designing high pass filters, or sorry, for designing digital differentiators, whereas the type 3 could be used for designing high Hilbert transformers and digital differentiators. Type 4 cannot be used for designing digital differentiators. They can be used only for designing approximation to Hilbert transformers. So we will see all those when we work out a few questions. And then we had seen certain properties of locations of zeros of linear phase FIR filters. We have seen that if Z0 is a 0 of h of z, then Z0 reached to minus and is also 0 of h of z. And likewise, you know that you need to complete the quadruplet constellation. The 0 constellation will be at Z star, Z inverse, and Z star inverse. So in the polar coordinates, you can write the 0 constellation at r e power j theta, 1 by r e power minus j theta, r e power minus j theta, and 1 by r e power j theta. And you have seen that the complex 0, when it lies on the unit circle, you will have zeros that occur in pairs, which are located at e raised to j theta and e raised to minus j theta. And if you have a 0 that is real and lies not on the unit circle, which means the 0 can be positive or negative. When it is positive, the angle theta equal to 0. When it is negative, the angle theta equal to pi. So you will have a pair of zeros located at r and 1 by r for theta equal to 0, and minus r and minus 1 by r for theta equal to pi. And finally, if you have a 0 at z equal to plus 1, then its own reciprocal is also at 1. So you can have a 0 at z equal to 1 to appear by itself, and a 0 at z equal to minus and also to appear by itself. So these are certain observations. We will use these observations to factorize the polynomial, so that you can factorize maybe a third order polynomial or a fourth order polynomial, etc. So we will see some examples today. What we will also look at is the zeros at plus or minus 1. So we see that for types 1 and 2, we see that for type 2, you see that you should definitely have a 0 at z equal to minus 1. You will be definitely having a 0 at z equal to minus 1. For type 2, you will be having a 0 at z equal to minus 1. For types 3 and 4, you definitely see that you will have a 0 at z equal to plus 1. And for the type 3, you will also see that you will have a 0 at z equal to minus 1. So for type 3, you will have a 0 at z equal to 1, and for z equal to minus 1. And thereafter, you can find the other roots by factorizing the polynomial by z minus 1 and z plus 1. So that way you can factorize the polynomial. So we will do some examples today. And now to start with, what we will do is, can you see the whiteboard? Can you
Yes,
see
sir.
the whiteboard?
Yes, sir.
Okay. Right. So we have a filter h of z given by 1 plus 2z raised to minus 1 plus 3z raised to minus 2 plus 2z raised to minus 3 plus z raised to minus 2. Now, can you tell me what type of filter is this? So this implies that you have h of n is equal to 1, 2, 3, 2, 1. So 1, 2, 3, 2, 1. What is the kind of filter that you have now? Roshan, are you there in the class today?
Yes, sir.
Let me see.
Yes, sir.
Roshan, what is the type of filter that you have here? What type of filter? What is the type of the filter that you have?
FIR.
Types 1, 2, 3, or 4? It's an FIR filter, but it's usually that's a symmetric FIR filter.
So the type 1.
Because
that
1, 2, 3, 2, 1. This is type 1. Because the length is equal to 5.
5. Odd.
Length is 5. So which means it's odd. So this is a type 1 FIR filter. So now let us see how we can implement this filter. Whether we can have any computational savings in implementing this filter. Okay. And we will try to represent this using the direct form representation. So we have x of n as the input to a filter structure. So you have z raised to minus 1. Then again you have another delay element. So we'll do it in the direct form 1 structure that you already have familiar with. And this is the last z raised to minus 2 that we have. So here you have this is x of n, this is x of n minus 1, x of n minus 2, and this is x of n minus 3, and finally this is x of n minus 4. So x of n is to be multiplied by 1. You see that x of n is to be multiplied by 1. This should be multiplied by 2. And this is to be multiplied by 3. This is to be multiplied by 2. And this is to be multiplied by 1. And then you have to add up all these. So this should be y of n. So this is a structure that you are familiar with. I hope this is okay. This is something that we had discussed earlier. So someone please tell me how many multiplications do you require to implement this filter? How many multiplications are required to implement this filter? Anthony Roy, എത്ര multiplication വേണം ഈ filter implement ചെയ്യാൻ? ഇത് clear ആണല്ലോ, വളരെ straight forward ആണ്. This is so x of n or this. പറഞ്ഞോളൂ, കേൾക്കുന്നുണ്ട്, പറഞ്ഞോളൂ.
Can't see. Hello.
How many multiplications are required?
One minute, sir. I can't see the screen now.
Is there an issue with the screen? Can
no,
someone get me a feedback?
ഈ അപ്ഡേറ്റ് വന്നതുകൊണ്ട് സ്ക്രീൻ പിൻ ചെയ്ത് വെക്കാൻ പറ്റുള്ള മാതിരിയായിരിക്കും.
എന്താണ് കേട്ടില്ല?
അല്ല, പണ്ടത്തെ ഇതല്ലല്ലോ, അപ്പൊ സ്ക്രീൻ പിൻ ചെയ്ത് വെക്കാൻ പറ്റുള്ള മര്യാദക്ക് എന്റെ സ്ക്രീൻ പോയി. അതേറാണ്. ഒരു മിനിറ്റ് സാർ.
ഓക്കെ, ഒരു കാര്യം ആ സമയം കണ്ട വേറെ ആരെങ്കിലും ഒന്ന് പറഞ്ഞു. ആൻസൺ പറയാമോ?
ഹലോ,
ആൻസൺ എത്ര മൾട്ടിപ്ലിക്കേഷൻ വേണമെന്ന് പറയാമോ? എത്ര മൾട്ടിപ്ലിക്കേഷൻ? ഞാൻ ഇതിനകത്ത് മൾട്ടിപ്ലിക്കേഷൻ എത്ര വേണമെന്നുള്ള ഞാൻ ഇതിനകത്ത് എഴുതിയിട്ടുണ്ട് കൃത്യമായിട്ട്. കാണുമ്പോൾ തന്നെ വായിച്ചാൽ മതി. ഇതിനകത്ത് വേറെ പ്രത്യേകിച്ച് യാതൊരു കാര്യം പറയാനില്ല. ജസ്റ്റ് റീഡ് ഔട്ട് ഹൗ മെനി മൾട്ടിപ്ലിക്കേഷൻസ് ആർ യു നീഡ് ഹിയർ.
5 ആണോ?
5 ആണല്ലോ, 5 തന്നെയല്ലേ കാര്യം. ബിക്കോസ് this has to be multiplied by 1, 2, 3, 2, 1. That's why 5 multiplication.
Okay.
So 5 multiplication. So this 5 multiplication, correction and the margin answer. And okay, you are multiplying by 1 here, and this also is being multiplied by 1. And you are multiplying by 2 here. Here also you have a multiplication by 2. Right? So why don't we combine these two and then multiply by 1? Why don't we combine these two and then multiply by 2? Can you appreciate this? So instead of computing it like this, what I will do now is something like this. So you know that the samples x of n, here also we have x of z. So x of z in z domain. So x of n and x of n minus 4 are to be multiplied by 1. So why don't we combine these? X of n and this is x of n minus 4. So here we have a multiplication by 1. This is a multiplication by 1. So we will multiply this by 1. So here what you have is, we will add these two. This is a summing point. So this remove this multiplication because these are just multiplications by 1. So we will add these two and multiply this by 1. Likewise, we have the next one, which is here. So I use a different color to emphasize this. These two are added together. And then it's multiplied by 2. Okay. And this, I will use a different color for this so that you can appreciate this. I will multiply this by 3. So this is multiplied by 1, this is multiplied by 2, and this is multiplied by 3. So what we'll do is we'll add all these 3 together, and this will be YU10 or YU10. What is the advantage here that we have? Answer. Multiplication, madam.
Sir, 3.
Multiplication.
Memory locations.
Multiplication memory location.
Okay, sorry.
Memory location and the another. What is the relation?
Sir, time korrekkan pattum.
Time time in or you just pass through the delay chain.
Okay.
That's time in the machine. This is not sample. So this has to pass through the delay chain. So x of n output. You require, let's say x of 4 is the current input. Time instant 3 ആണ് there. X of 3 ആണെങ്കിൽ നമുക്ക് അതിന് മുമ്പുള്ള x of 2 വേണം, x of 1 വേണം, x of 0 വേണം. ഇത്രയും സാധനങ്ങൾ കിട്ടിയാൽ മാത്രമേ എനിക്ക് ഇപ്പോഴത്തെ ടൈം ഇൻസ്റ്റന്റ് എനിക്ക് കിട്ടത്തുള്ളൂ. ശരിയല്ലേ പറയാൻ? ഞാനിവിടെ ഇപ്പൊ x of 3 ആണ് ഇൻപുട്ട് എങ്കിൽ ഇവിടെ എന്ത് വരും? This is x of 2, this is x of 1. Sorry, this is x of 4 is input. If this is x of 4, then this is x of 4. Then you will have x of 3 here, x of 2 here, x of 1 here, and x of 0 here. അപ്പോൾ എനിക്ക് പഴയ x of 0 വരെയുള്ള സാമ്പിളുകൾ കയ്യിലുണ്ടാവണം. I require the previous 4 samples in addition to the present sample. All those have to be added in this fashion to produce the output YO4. ഇതെല്ലാം കിട്ടിക്കഴിഞ്ഞാൽ YO4 കിട്ടത്തുള്ളൂ. Only then you will get YO4. Answer, is this clear?
Yes, sir.
So delay എന്ന് പറയുന്നത് എന്തിനെ ഡിപ്പെൻഡ് ചെയ്യും? Delay depends on the number of z raised to minus ones in the delay chain. So that is why it's called as a delay chain. If the delay chain is longer, you will require more time for the signal to pass through the delay chain. You can very easily neglect the time required for a multiplication or an addition because they are actually clock independent operations, whereas this delay are clock dependent operations. Multiplication and addition are just dependent on the propagation delay of the device that you are going to use. So that will not take any additional delay. So what it will do is a multiplier will mean you will require a hardware in the you require a multiplier hardware in the overall circuit. So that will result in a multiplier hardware will result in more chip area. So if you have, instead of earlier we had 5 multipliers, now you will have 4 multipliers. So that will result in, or you will have 3 multipliers. That will result in lesser chip area and therefore more power savings. ശരിയല്ല? Multiplication എണ്ണം ഏകദേശം പകുതിയായിട്ട് കുറഞ്ഞു. Is it understood?
Yes, sir.
Okay. So this is a linear phase structure for type 1 FIR filter. So let me look at a type 2 FIR filter. This is a type 2 FIR filter. So I will change the coefficient values. So 1 plus 2 z raised to minus 1 plus 2 z raised to minus 3 z raised to minus 2 plus z raised to minus 3. So the samples are therefore 1, 2, 2, 1. So what type of filter is this? Anthony Roy, what type of filter is this? Is it a linear phase filter?
Sir, type 2.
Type 2. It's a linear phase filter, right? Okay, very good. Either a linear phase filter or linear phase. I'm going to draw some filter. 1, 2, 3, 1. Is it a linear phase filter? Anthony Roy? Is this linear phase?
Hello. അല്ലാന്ന് തോന്നുന്നു.
അതെന്താ അല്ലാത്തത്? എന്താ അങ്ങനെ തോന്നാൻ കാര്യം എന്താ? അത് ക്ലാസ്സിലൊന്നും കയറാതിരിക്കുന്നുണ്ടാണ് പ്രശ്നം. ലീനിയർ ഫേസ് ആവണമെന്നുണ്ടെങ്കിൽ ഒരു കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യണം നമ്മൾ നേരത്തെ പറഞ്ഞിട്ടല്ലോ. അതെന്താണ് ആ കണ്ടീഷൻ? ലക്ഷ്മി, ദിസ് ഇസ് എ ലീനിയർ ഫേസ് filter.
Yes, sir.
This is a linear phase filter. Are you saying that this is a linear phase filter? For
Yes.
linear phase, what are the conditions to be satisfied? You require either symmetry or
asymmetric.
anti-symmetry.
Yeah.
Anti-symmetry.
Sorry, sir.
Is it symmetric or anti-symmetric?
This is symmetric.
1, 2, 3, 1. Is that symmetric?
Yeah. Yes.
What do you mean by symmetry? So if you have 1 and 2 here, the symmetric filter should be having this. So
Oh,
symmetric.
sir.
1,
No,
2.
because it's 3.
No, because it's 3, it's symmetric. It's not symmetric.
It's an anti-symmetric.
What about 1, 2, minus 2, minus 1? What about this? Is it a linear phase filter?
And
This
the
is minus
minus
2.
2 would be like below the line. So
1, 2, minus 2, minus 1. Just tell me whether it's symmetric or anti-symmetric.
it's an anti-symmetric.
Anti-symmetric, right?
Come
So is
below.
it linear phase or non-linear phase? Is it linear phase
Since
or
it's
non-linear phase?
anti-symmetric, it has to be linear.
You will get linear phase.
Yeah.
Now, did I ever say that you can design only symmetric or anti-symmetric filters with the FIR filters? Did I ever say that you can design only anti-symmetric or symmetric FIR filters? Was it ever mentioned? Did I ever say that?
No.
Will you be able to design a filter like this? 1, 2, 3, 4. This is my FIR filter that I want to design. Can you design an FIR filter? The answer is that
Yes,
you can design an FIR
you can
filter.
design. Yeah.
You can design an FIR filter. In certain cases, you might end up with these kind of filters which are not symmetric or anti-symmetric.
Yes.
But you have the freedom to design. You have the freedom. So listen to this very carefully. You have the freedom to design symmetric or anti-symmetric filters that give you linear phase response, or in other words, that does not have any phase distortion. So you can design filters without any phase distortion if you are going to use FIR filters. It does not mean that you cannot design symmetric, non-symmetric or non-anti-symmetric filters. You can design these kind of filters also. In certain applications, you will definitely result in this kind of filters. For example, filters for multi-rate signal processing, such as you will not see more in detail about that. In certain cases, you will definitely end up with these kind of filters. You can have linear. So I should be actually saying that you can have linear phase FIR filters. You can have linear phase FIR filters, right? So now let us look at the filter that you have in question and try to implement this filter. So this is a type 2 filter. So likewise, you can think of an X of n as the input, X of Z being its Z transfer. How many delay levels you require now? You require 3 delay levels. So these are raised to -1. And this is to be multiplied by 1. This is to be multiplied by 2. This again is to be multiplied by 2, and this is to be multiplied by 1. So what we'll do is we will combine these two multiplications, these two as a single signal by adding these two signals, and then we will multiply this by 1. And then what we will do is we will combine these two signals, we will add these two signals, and then we will multiply this by 1, 2, and then we will add these two. This is your output signal. So this is Y of n and the Y of Z. This is understood. So this is your type 2 filter. Likewise, let me also look at this filter. So 1 plus 2z raised to -1 minus, so this would be 1 plus 2z raised to -1 minus 2z raised to -1 minus z raised to -3. So then my filter is 1, 2, -2, -1. So what kind of a filter is this? Let me ask someone. Mahima, what kind of a filter is this? What type of a filter is this? Mahima ഉണ്ടായിരുന്നല്ലോ ക്ലാസ്സില്. Mahima ji. So please unmute yourself and answer the question. Mahima ji, have you left the class? So shall I mark Mahima is absent? Okay, Mahima, please answer this question. What about this filter? Is it H of Z? Is it type 1, type 2, type 3, or type 4?
So I think it's type 4.
Why do you say it's type 4? What is the reason for that?
Even an anti-symmetric.
anti-symmetric and
Even.
the length is even, right? So the filter is anti-symmetric and the length is even. Filter is anti-symmetric and the length is even. So which means you have constant group delay but not constant phase delay. So how will you implement this filter? So this can also be easily implemented just like your type 2 filter. The only difference is that this has to be multiplied by -1. So here you need a multiplication by -1, right? And here you need a multiplication by -1. We should do multiplication by -1. This is understood? So this is x of n, x of n minus 1, x of n minus 2 is multiplied by -1. And the whole thing will be multiplied by 2. And here x of n minus 3 is multiplied by -1. And this is again multiplied by 1 here. So you see that for multiplying by -1, you don't actually require any multiplication at all. Because you have seen that in the hardware implementation, you only need to invert the sign bit. So if this is sign bit, and if the rest of the bits are the magnitude bits, say for example, you have a 1-bit sign bit and 7-bit magnitude, so you can represent up to plus 2 raised to 7 to minus 2 raised to 7. So this is the range of integers that you can represent. So if this is how you represent the number, you don't have to actually perform any multiplication at all. You need to complement the sign bit. If this was 0 earlier, now change the sign bit to 1. Is that understood? If this is 0, you only need to change the sign bit to 1. If this is 1, you only need to change the sign bit to 0. So, Mahima, is it understood that you don't need to do any multiplier logic? You don't need to implement any multiplier logic for multiplying by -1. Is that understood?
Yes, sir.
Okay, so how many multiplications are there for required to implement this? How many multiplications are required to implement this? You require just 2 multiplications. Is it okay?
Yes, sir.
Okay, so likewise, we can design the type 3 filter as well. The principle is the same. We can design the type 3 filter as well. So now I want you to look at this example, so which I am going to give you now. So the question would be slightly different. Let us see how you can approach this. So this is a filter that you are given. So h of z is equal to 1 plus 2z raised to -1 minus 2z raised to -2 minus z raised to -3. So let me switch to the PowerPoint presentation. So you have seen this observation that for the type 4 filter, which is what we have seen now, for the type 4 filter, you will have a 0 at z equal to +1, right? For a type 4 filter, you have a 0 at z equal to +1. So let us go back to the whiteboard now. So you can write h of z as your type 4 filter. So we'll write this as z cube plus 2z squared minus 2z minus 1 divided by z cube. So divided by z cube, right? So where are the first of all, let us look at where are the poles of this filter located. Where are the poles of this FIR filter located? അതൊരു വളരെ സില്ലി ക്വസ്റ്റ്യൻ ആണ്. കാരണം നമുക്ക് നേരത്തെ അറിയാം FIR ഫിൽറ്ററിന്റെ പോൾസ് എവിടെയായിരിക്കും ഉണ്ടാവുക. FIR ഫിൽറ്ററിന്റെ പോൾസ് എവിടെയായിരിക്കും ഉണ്ടാവുക? At the origin. So the FIR filter will have poles located at the origin. That is why the FIR filter is always stable, because the origin is contained at exactly the midpoint of the unit circle. So it's always stable. Now, where are the zeros? What about the zeros of this filter? From what we have discussed just now, you know that there is a 0 at z equal to +1, right? You have a 0 at z equal to +1. For the type 3 and type 4 system, you have a 0 at z equal to +1. So what does it mean? You have a 0 at z equal to +1. So which can be verified by putting z equal to 1 and c. So 1 cube plus 2 into 1 minus 2 into 1 minus 1. So that is equal to 0. So you will have a 0 at z equal to +1. That is confirmed. So which means you will be able to factorize z cube plus 2z squared minus 2z minus 1 by z minus 1, because you have a 0 at +1. So z cube plus 2z squared minus 2z minus 1 can be factorized by z minus 1. That is what we have said. So this should be z squared. So z cube minus z squared. So that should give you 3z squared minus 2z. So that should be plus 3z. So 3z squared minus 3z. That should be z minus 1 should be 1. So z minus 1, so you don't have any remainder. So remainder is 0. So this can be factorized as therefore. So this we can factorize as this is equal to z cube plus 3z plus 1 into z minus 1 by z cube. Or in other words, you can write this as 1 plus 3z raised to minus 1 plus z raised to minus 2 into 1 minus z raised to minus 1, where I have divided this by z squared and divided this by z. So this is your h of z. Now, if you are given a type 4 filter like this, for your exam, you might be asked to implement this as a cascade of a second order system followed by a first order system. So which means if you directly go on to factorize this third order polynomial, you might not actually end up factorizing this polynomial. So that could get, things could get difficult. Because you know that it's a fourth order polynomial and you know that you will have a 0 at z equal to plus 1, then you should be able to factorize this like this. This is done by observing that this is a type 4 polynomial and that you will have a 0 at z equal to plus 1. So if you are asked to factorize this in terms of a second order system and a first order system in series or in cascade, this is the way in which you can factorize. Is it understood? So if I move on to a type 3 filter, for example, if I look at a type 3 filter, so now what will a type 3 filter look like? A type 3 filter definitely has to pass through the origin at the midpoint. So you'll have this will pass through the origin at the midpoint. So we'll have 0 z raised to minus 2. So I will skip that and write plus or rather minus 2. So minus 2 z raised to minus 3 minus z raised to minus 4. So this is my filter. h of z is equal to 1 plus 2z raised to minus 1 minus 2z raised to minus 3 minus z raised to minus 4, which I can write as this is my filter h of n given by 1, 2, 0, minus 2, minus 1. So if you have a filter like this, then from the previous slide itself, you have seen that you have a 0 at z equal to 1. For type 3 system, you'll have a 0 at z equal to 1, and you'll have a 0 at z equal to minus 1. So you have already found out two roots of the system. So which means this can be factorized as, anyhow, this can be factorized as z minus 1 into z plus 1, because you have a 0 at plus 1 and at minus 1 into a polynomial, so which we will call as h2 of z, because the polynomial has got an order of 2 divided by z raised to 4. This is your h of z. So you have to find out what is h2 of z by dividing this by z squared minus 1. So divide this by z squared minus 1 to find out what is h2 of z. So that gives you a very easy method to factorize certain kinds of polynomials. So if you have a symmetric polynomial, if you have an anti-symmetric polynomial, definitely you can say that you have a root at z equal to plus 1. And if the anti-symmetric polynomial has got a length that is odd, you can definitely say that you have a 0 at z equal to plus 1 and a 0 at z equal to minus 1. So that's a very helpful observation. So that helps you in factorizing higher order polynomials. So in this case, you have a fourth order polynomial, which you have very easily factorized by observing that it is anti-symmetric. Fourth order polynomial, which you have factorized, observing that it is anti-symmetric, and you see that the central sample is a 0. So you might be asked to implement this as a cascade of two first order systems and a second order system. So without this observation, you might go the whole day trying to factorize the fourth order polynomial. So the observation that you have a 0 at z equal to plus 1 and z equal to minus 1 will help you to factorize the polynomial in this manner. Okay. Right. So that is all about the linear phase FIR filter structures. So now what I would like to bring to notice is we are going to start the design of FIR filters. And we'll see what is the principle for design of FIR filters. So what are FIR filters, by the way? How do you expand FIR? Let me pick someone, and this is a very basic question. Jitin PK, Jitin, Jitin, please unmute your mic and please expand what is FIR. I'm only asking you to expand what is FIR. Jitin ക്ലാസ്സിൽ ഉണ്ടോ? Jitin FIR എന്നുള്ള എക്സ്പാൻഡ് ചെയ്യാം. എന്താണ്? അത്രേ ഉള്ളൂ. സിമ്പിൾ ക്വസ്റ്റ്യൻ. How do you expand FIR? FIR എങ്ങനെ എക്സ്പാൻഡ് ചെയ്യും?
Sir, finite impulse
response. അത്രേ ഉള്ളൂ. FIR എന്ന് പറഞ്ഞാൽ ഫൈനൈറ്റ് ഇമ്പൾസ് റെസ്പോൺസ് എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം എന്താണ്? ഫൈനൈറ്റ് ഇമ്പൾസ് റെസ്പോൺസ് എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം എന്താണ്? ഇമ്പൾസ് റെസ്പോൺസിൽ എന്താണ് ഫൈനൈറ്റ്?
Sir, ലീനിയർ കറക്റ്റ് ആയിട്ടുള്ള, അതായത് ഫൈനൈറ്റ്സ് ആയിട്ടുള്ള വാല്യൂസ് ഇമ്പൾസ് റെസ്പോൺസ് ആയിട്ട് വരുന്ന സാമ്പിൾസ്.
അല്ലാത്തതിനൊക്കെ ഇൻഫൈനൈറ്റ് സാമ്പിൾസ് ആണ് ഉണ്ടാവുക. ഇൻഫൈനൈറ്റ് ആയിട്ടുള്ള വാല്യൂ ആണ്. ഒരു സാമ്പിളിന്റെ വാല്യൂവിനെ കുറിച്ചാണ് പറയുന്നത്, ഒരു സാമ്പിളുകളുടെ എണ്ണത്തെ കുറിച്ചാണ് നമ്മളിപ്പോ പറയുന്നത്. എന്തിനെ കുറിച്ചാണ് പറയുന്നത്? ഫൈനൈറ്റ് ഇമ്പൾസ് റെസ്പോൺസ് എന്ന് പറഞ്ഞാൽ സാമ്പിളിന്റെ വാല്യൂ ആണ്, സാമ്പിളുകളുടെ എണ്ണമാണ്.
ഡ്യൂറേഷൻ സാമ്പിളിന്റെ
ഡ്യൂറേഷൻ പറഞ്ഞാൽ സാമ്പിളുകളുടെ എണ്ണം. You are looking at the number of samples. Right?
Yes, yeah.
Okay. So you are looking at the number of samples when you are talking of FIR or IR filters. For IR filters, you say that you have infinite number of samples. Say, for example, 1 by 1 minus 0.5 z raised to minus 1. Is it an FIR filter or an IR filter? Within continue the FIR on IR. FIR or IR. And the class like within the is it FIR or IR? പറയാം. ജിതിൻ ഉണ്ടോ അത് പോയാ?
അത് FIR.
അത് FIR ആണ്. ആരെങ്കിലും ഒന്ന് പറയാം, ക്ലാസ്സിൽ ശ്രദ്ധിച്ചിട്ടുള്ളവരാണെന്ന് പറയാമോ? ലക്ഷ്മി, ഇത് FIR ആണോ IR ആണോ ലക്ഷ്മി എന്ന് പറയാമോ?
Sir, it's an IIR filter because it's a ratio.
It's a ratio, it's an IR filter. But to establish that it's an IR filter, let us
Stability, sir. It involves the unit circle.
You have
it's inside the unit circle.
You have poles inside the unit circle. It's a stable IR filter. You have poles at Z equal to +5, right? You have a pole at Z equal to 0.5, plus 0.5. So, whereas for FIR filters, you usually have poles at the origin.
At the origin, yeah.
Let us try to establish that it's an IR filter. So for that, what we'll do is we'll divide this by 1 divided by 1 minus 0.5 z raised to minus 1. So 1 by 1 minus 0.5 z raised to minus 1. If you divide this row, so I will write this as 1 minus 0.5 z raised to minus 1. So what I have here is plus 0.5 z raised to minus 1. So for that I have to multiply this by plus 0.5 z raised to minus 1. So again now this becomes plus 0.5 z raised to minus 1 minus 0.5 squared. So that is 0.25. So I'll just write this as minus 0.5 squared z raised to minus 2. Right?
Yes.
So what will be this?
0.5 square is
Plus 0.5 the whole square is a raised to minus 2 again, so which means I have to again multiply this by 0.5 the whole square. Right.
Goes on. So
is a raised to minus 2. So plus etc. Like this. So which means my filter that I have here represented like this here. Actually, the filter 1 by 1 minus 0.5 z raised to minus 1 by log division has been established as the filter 1 plus 0.5 z raised to minus 1 plus 0.5 the whole square z raised to minus 2 plus 0.5 the whole cube z raised to minus 3 plus etc. Or in other words, you have your filter h of n as equal to 1. Here you have your origin, and this is 0.5. Next one is 0.5 the whole square, and this is 0.5 the whole cube, etc., etc., etc. Up to how many samples will be there?
infinite samples.
There will be infinite samples, and therefore this is an IIR filter. That is why this is an IIR filter, right?
Okay.
So this is your IIR filter. Okay. Now, the filter that you actually need are ideal filters. Say, for example, if you require an ideal low-pass filter, so if you have an ideal low-pass filter, you know how the frequency response of the ideal low-pass filter looks like. So I will draw a discrete frequency response, and you know that the discrete frequency responses are periodic. I'll just draw the magnitude response. So I will mark plus pi here and minus pi here. So maybe this is plus the digital frequency plus omega c. So this is omega c, which is the cutoff frequency, and this is minus omega c, which is the negative cutoff frequency. So this is the ideal filter that you have to realize. So this is your brick wall. This equals your brick wall frequency response. Brick wall frequency response. And we will assume that this is a zero phase response, that is the phase is along the x-axis. So there is no phase delay. If the phase is along the x-axis, there will not be any phase delay. So since it is periodic, I have to actually draw a cycle here. That will be something like this. This is a cycle here. Cycle here. And here. So we have something here also. So this is a periodic frequency. So you know what will be the frequency response of this filter. Sorry, this is the frequency response of the filter. And you have actually solved this in the subject signals and systems when you studied your discrete time Fourier transforms. I remember taking this very particular question in the class. So what you will finally end up is a single-like frequency response. So if this is your h of e for j omega, if we compute the inverse dTft, then you will see that it's somewhat like this. So if I draw the envelope, that will look like a C function. If I draw the envelope, it will look like a C function. So we will have samples from minus infinity to plus infinity. This is how maybe you will be having your samples. Anyhow, what I want to point out here is you will have samples from minus infinity to plus infinity. Do you understand this? So which will be your, if you mark this as your zeroth sample, this is zeroth sample. So this is the amplitude of the zeroth sample. You will have samples starting from minus infinity to plus infinity. Now, please tell me whether it is FIR. This is filter FIR. Mahima ഇത് പറഞ്ഞ FIR ആണോ ഉള്ളത്? മഹിമ ജി പോയി ക്ലാസ്സിന് പോയ അത് FIR ആണോ IIR ആണോ? ഞാനിപ്പോ വരച്ചിട്ടില്ല. Jiben wrote, Jiben.
Yes, sir. Hello.
Now, are you able to see? Either FIR or IIR. ഈ സാമ്പിൾ എവിടെ നിന്നാണ് തുടങ്ങുന്നത്? സി എവിടെ നിന്നാണ് സാമ്പിൾസ് സ്റ്റാർട്ട് ചെയ്യുന്നത്? മൈനസ് ഇൻഫിനിറ്റി എന്നല്ലേ തുടങ്ങുന്നത്? അല്ല, എവിടം വരെ പോകുന്നു?
Plus infinity.
എവിടം വരെ പോകുന്നു? പ്ലസ് ഇൻഫിനിറ്റി വരെ. So how many samples are there?
Infinity.
Infinity samples. Now infinity number of samples.
Yes.
Okay, I agree with you. And now what about can you call it as an IER filter in our conventional sense? IER filters, whatever we have seen, IER filters, they start at some point and extend up to plus infinity, right?
Yes, sir.
All but this starts at minus infinity. So this sequence does not have any beginning or an end.
Yes.
It starts from minus infinity, goes up to plus infinity. So anyhow, which means that this filter cannot be implemented. We said that this filter is not causal and therefore cannot be implemented. Okay, because because it is what?
Non-causal signal. To implement, we need to make it causal.
This filter is a non-causal filter. So I will not call this signal as a non-causal signal. Or maybe I can say that this h of n is this is your h of n. So H of n is a non-causal signal, which means that my system is a non-causal system.
Okay.
My system is a non-causal system, right? So that I can agree to.
Okay.
Now, we are going to explore a way to approximate this so that we can maybe make this system a causal system, or at least a finite duration system. So for that, what I'm going to do is I'm going to look at this signal through a window.
Yes.
You see that the amplitudes go on decreasing towards plus infinity and to minus infinity. So maybe, suppose if I look at this signal through this window, so maybe I'll put the window here. What I will do is I will look fully at these angles.
It's a
Okay.
rectangular window.
This is what we call as a rectangular window. This is what we had discussed earlier. This is your rectangular window. So what we do is we'll look at this signal through a rectangular window. Right?
Yes, sir.
Okay. So we will look at this signal through a rectangular window. Now, within this rectangular window, we will rub off the rest. So now you can say that this signal has a beginning and an end. So this has got the first samples from here. The first sample starts here, and maybe the last sample is goes up to here. So this is your last sample. So maybe I'll mark this number as minus 100. This as plus 100. So I'll mark random number. So how many samples will H of n have now? Jibit. H of
Sir, 200.
sample. I've taken a window. So H of n will have how many samples? This truncated H of n will have how many samples?
200. 201, including that 0.
201 samples. 201 samples, right? From minus 100 to plus 100. So the truncated H of n, so I will now represent it as HT of n. So this is a truncated H of n, or I can maybe call it as the windowed H of n, or I can also call it as HW, which is the windowed H of n, or truncated H of n. So which is actually the original H of n multiplied by a W of n, right? Windowing function. So W of n is your windowing function. And you have seen that there are several choices for the windowing function. You can have a rectangular window. Maybe you can look at a triangular window. You can look at other shapes of the window. Each window bring into play its own advantage. So which we are going to see later over. But anyway, the principle is to view the signal that starts from minus infinity and ends at plus infinity through a window of some finite duration. Here we are taking a symmetric window of duration 201. We are taking a symmetric window of duration 201. Is it understood?
Yes, sir.
Okay. Now, what we will again do is we will make this causal by designing the FIR filter. So I will call this as FIR of n as equal to HW of n minus 100. Okay, so what does it mean? We are going to shift this by 100 samples to the right. Is it understood? We will shift this by 100 samples to the right.
Right.
So what we'll do is now we will relabel the indices. We will just relabel the indices. The indices will be relabeled as starting from 0 and going up to what? You have 201 samples, so going up to 200, right?
Yes.
Okay. So how many samples are there? This is 201 samples. So this is the filter now that you are going to design. This is the filter that you are going to design. And now because of this shift by 100, this will introduce a linear phase shift. This will have a linear phase response because of this shift by minus 100. See, why do I say that this is linear? It is because I have selected a window that is symmetric with respect to the origin. So that the windowed sequence is now a symmetric sequence. For this example, the windowed sequence is a symmetric sequence. So therefore, it has to be either type 1 or type 2. It has to be either type 1 or type 2. Most likely, it is going to be type 1 because our sample at 0. So this is a type 1 filter. We have windowed this so that the windowed sequence is symmetric, and then we have made the windowed sequence for
So the window is 1 for.
Okay. Yes, please.
So the magnitude of the window function is 1, right? For 0 to 200.
The magnitude of the window function here is taken to be equal to 1.
Okay.
This is taken to be equal to 1. So this is a rectangular window. We call this as a rectangular window. I have different possibilities for the windows. Maybe I can look at a different shape of the window. Like for example, I can look at a window like this. So this will amplify the central sample by a large value, and it will amplify the samples on the left and right of the central samples by a smaller value, and will finally amplify the end samples by 0. So this is known as the triangular window. It's also known as the Bartlett window. Bartlett. Anyhow, we will be seeing in greater detail Bartlett window. That we will see when we see what is the principle behind. As we see more and more good examples on FIR filter using windowing method, we will see different kinds of windows. We will see why other kinds of windows are required. Now, this is your process by which you can convert your ideal filter to linear phase FIR. Now, since you have a multiplication here, what happens in the frequency domain? Now, Meenakshi, what will happen in the frequency domain? We have multiplication in the time domain. Let us try to write on the frequency domain equation. So we will write SW of e raised to j omega. What will be this equal to, Meenakshi? This is equal to, you have a multiplication in the time domain. Multiplication in the time domain is
convoluted in the frequency domain.
Right, that's very good. So this is therefore a convolution in frequency domain. H of e power j omega convolved with the W of e power j omega. So definitely the shape of the filter is going to change. The shape of the magnitude or the amplitude response is definitely going to change from H of e power j omega to HW of e power j omega as decided by the window frequency response W of e power j omega. So we will see the rest tomorrow. But when you come for the class tomorrow, I want you to work out the following question. So this is an assignment. I will put up the question on the model assignments. The first question is, you can take down the question if you want. Anyhow, I will be uploading this tomorrow. So what you can do is you can find out the answer to all of this. So if you have ideal low pass filter such that H of e raised to j omega is equal to 1 for mod omega less than or equal to omega c is less than pi. So what does it mean? Mod omega less than or equal to omega c less than pi. So when mod omega is between pi and when omega c is between mod omega less than or equal to omega c, mod omega less than or equal to omega c, and omega c is less than pi. So it means that you have this is omega c, this is minus omega c. So when mod omega is less than or equal to omega c, so you are looking at this range of frequencies, the value is equal to 1. Okay, so this value equal to 1, and it's equal to 0 for mod omega greater than omega c, right? Mod omega greater than omega c. So this is plus pi, this is minus pi. So this value is equal to 0. So this is your ideal low pass filter. So find out the impulse response h of n.
Okay.
Okay, that's your first question. Which you have. This is something that we done in previous semester when I told sequence and systems. The second that you need to work out is find out the impulse response of the ideal high pass filter. This is your ideal high pass filter. So start from minus pi, goes up to plus pi. And this value is minus omega c. This value is plus omega c. And this is equal to 1. Find h of n for this filter. That's the ideal high pass filter. Okay. So now let us look at the ideal band pass filter. Ideal band is something like this. You have two cutoff frequencies, omega c1, or I'll just call it as omega c1, and this is omega c2, and this is pi. Likewise, I have a minus omega c1, minus omega c2, 1 minus omega c2, and this is minus pi. Find the impulse response of this filter. Find h of n for this filter. So this is your ideal band pass filter. So this magnet is equal to 1. Finally, look at the ideal band stop filter. Ideal band stop filter is something like this. You have an ideal band stop filter that should stop the filters from bands from omega c1 to omega c2. This is minus omega c1 to minus omega c2. This value is equal to 1. So find h open for this. So I've given you 4 questions. You have to work this out and be ready with the answers when you come for the class at let's say 6 o'clock tomorrow, 6 o'clock evening. Is that okay with you? നാളെ 6 മണി എങ്ങനെയുണ്ടാവും? Is that okay for 6 o'clock tomorrow?
Sir.
Answer.